Hello, I'd like to talk a little bit about problem solving in the introductory physics sequence. And helping me with some mellow relaxing is the dog. More important in this case is the problem solving template. So, first off, I want to talk a little bit about what we'll be doing here. So, the OpenStax book in section 2.6 has, so that section is entitled Problem Solving Basics for One-Dimensional Kinematics. And they have a step-by-step problem solving method. So examine the situation to figure out what physical principles are involved, make a list of the knowns, either that are specifically stated or that can be inferred, figure out what needs to be determined, so the unknowns, find an equation or set of equations, substitute the knowns into the equation, maybe substitute equations into each other. And then step 6, check to see if the answer is reasonable. So I converted that into a problem-solving template. It has essentially 3 parts: a sketch, solve, and check. So for the sketch, we can make that a little bit bigger. I tried to make it fairly general, generic that could be used throughout the series. Some things aren't quite as appropriate, like, so the simple diagram is always important, showing the important points in the motion of the problem. There might be some problems in which there isn't any motion. So if you've got a chandelier hanging from the ceiling and we're trying to analyze the forces on the cables that are holding the chandelier up, there's not going to be motion there. So just because it's listed doesn't mean you need to force something in. And then at the bottom, draw motion-free body and or energy diagrams as appropriate. Those are not always appropriate. Establishing a coordinate system, the second point, is almost always important. And the problem-solving template is best used for problems that are multi-step. If you've got a problem where A times B equals C, you're given A and B, you need to find C. It doesn't really make sense to do this elaborate problem solving setup. So the sketch, that guides you, and then we've got space here for the sketch. I mentioned before listing the knowns and the unknowns. Some of the knowns are specifically stated in the problem, that the initial velocity is 10 meters per second. The final position, a person runs 400 meters. Some of the knowns might be not specifically stated. So if you're dropping something on the surface of the earth from the top of a building on the earth, the problem might not state g, the acceleration due to gravity near the surface of the earth, but that's still a known if it says this thing is happening on earth. Or if it doesn't say it's happening on earth, you can probably assume it is if it's a building and you're dropping a ball. If the person is running 400 meters, probably the best assumption is a number line that starts at 0 and ends at 400. So you'd know the initial position then is 0 meters. The final position is 400. So things like that. And then the unknowns, you don't have to list every single unknown in the world. You can definitely list the target variable, the unknown that you want to solve for, and maybe 1 or 2 unknowns that might show up along the way. And then the problem-solving method in the OpenStax book talks about listing the equations. So list those. And then make any sort of substitutions, plug formula A into formula B, and then finally plug in the numbers. So it's best to not plug in the numbers until the very end. So you have an algebraic solution and then plug in the numbers, because the algebraic solution is a general solution to any situation related to those parameters. So if you've got another situation where you're on a different planet, you can plug in a different value for g. Or you're running not 400 meters, but 800 meters. So you can plug in 800 meters. If you plug in along the way and solve the little mini equations, For one thing, that's more of a chance for error. The more times you plug in numbers, the greater the chance that you're going to plug something in wrong. But then second, you're not really getting a general solution at the end. And then the last part is checking whether your answer is reasonable. And I give you some ways you can do that. Those aren't the only ways, but you can justify using some order of magnitude calculations. So if the person is running 950 meters, you could say, well, that's about 1,000, 10 to the third, and plug in factors of 10. You can compare to other known values. If the problem is asking for the final velocity of an Olympic sprinter, that's a human, a fast human. So if your answer is 1 meter per second, that's probably too slow for an Olympic sprinter. It is too slow. If your answer is 1,000 meters per second, that's too fast for an Olympic sprinter. And then you can do a unit analysis as well. Significant figures are okay. In and of themselves, they don't really check the quality of the answer, but I usually count those as sort of a secondary or tertiary check. And then I have a rubric as well, but I'll show you that when we're going over a problem. So I'm going to show you the solution to a problem from one of the physics classes. So we've got a sprinter accelerating from 1.75 meters per second to 7.75 meters per second over a distance of 22.5 meters. This is using our online homework system, Expert TA. When you see numbers in red, those are randomly generated. So not everybody is going, in fact, nobody else will be getting these numbers. This is just the first random generated set. And we want to calculate the average force that the sprinter exerts on the track if he encounters a headwind that exerts a certain force against him. So this right now is getting into work and kinetic energy. So that is the problem. And here is our solution. I wanted to draw some things. Oh, there we go. Finally got to it. Draw. There we go. All right. So draw a simple diagram. I've done that. Here is our simple diagram. And I've drawn the free body diagram. Show the important points in the motion. I've got the beginning point and the end point. I've got the position, the initial position and initial velocity labeled. I've got the final position and the final velocity labeled. So here's one of those times where I mentioned it doesn't say it starts at 0 and ends at 22.5, but it says the person runs 22.5 meters. So it makes sense to say that the initial position 0, final position is 25. And here I just said, okay, delta x, so the change in position is 22.5 meters, but then I labeled those here. Our coordinate system, so up and down is y, positive x direction is to the right, which makes sense. And I didn't do any sort of a motion or energy diagram, not really needed here. So I made a note here, the force that the sprinter exerts on the track is equal and opposite to the force of the track on the sprinter. So they're asking for the force that the sprinter exerts backwards on the track. We're going to be figuring out what the work is that the track does on the sprinter. And so I've listed the other unknowns, and then our unknown, the target variable, is the force of the track on the sprinter. And all the formulas, so basically just the fundamental ones. So this uses the work equals change in kinetic energy, so the work done by everything on the sprinter. So I've defined the system as the sprinter. So the wind is exerting a force on the sprinter. So the wind is doing work on the sprinter. The track is doing work on the sprinter. and the frictional force. So the track is doing work on the sprinter when it's pushing the sprinter parallel to the track. The track is also holding the person up from falling down towards the center of the earth, but that doesn't do any work. So this force and this force are perpendicular to the motion of the sprinter. So they don't do any work on the sprinter because the work is force times the displacement or the distance over the work, or over the distance, the displacement over which the force is being applied times the cosine of the angle between them. And for a 90-degree angle, the cosine is 0. And then here's just the general formula for kinetic energy. And two things then are doing work on the sprinter. The track, due to the, I'm just going to keep doing the wrong one. I was going to change the color, but that's okay. Forget how to do that momentarily. So the track and the wind are doing work on the sprinter. The track is doing positive work on the sprinter because it's in the same direction as the motion. The wind is doing negative work. That's just a little preview. So notice if I make my diagram really well and I print out these numbers well, I don't even need to look at the problem again. I can solve the problem just from this because I know I need to solve for f sub track. And once I write down the formulas that I need, I shouldn't need to look at the book anymore. So right now, all the knowledge I need to solve this problem is on the screen in front of us. So first I use the work equals change in kinetic energy formula. And then I use the relationship between work and each of the forces. And I already talked about that. The cosine of theta, the track is pushing in the direction of motion. The wind is pushing opposite the direction of motion. So then I plug these two things into here. And because I want the force of the track, the force that the track exerts on the sprinter, I'm going to isolate that. So first I subtract this from both sides. And then I divide. So then I end up with this. And then I divide both sides by d. And we get that right there. And then this step here is just simplifying. So I factor out the 1/2 m and then factor out the d from this work done by the wind. And notice we get the negative number here because the wind is doing negative work. It's essentially slowing the person down. And plug all those numbers in and we get the force that the track exerts is 105 newtons. So first off, does that make sense? Well, the force of the track on the person is equal in strength and opposite in the direction of the force that the person exerts on the track. So if we convert newtons to pounds, 1 pound is about 4.5 newtons. That equals 23 pounds of force. And if it's not a familiar number, I would not accept what I'm about to say here as justification, but it seems highly reasonable that an average athlete can push off with 23 pounds of force. So if a person can do a single leg bodyweight squat, if a 150-pound person does a single leg bodyweight squat, they're basically pushing off with 75 pounds of force, right? So because they're actually pushing off with their full body weight. If you're doing a double leg squat, is where I was thinking when I started the sentence. 150-pound body weight, each leg is pushing up with 75 pounds. So most people can do a body weight squat. In fact, most people can do many body weight squats or even weighted squats. So 23 pounds, in a sense, maybe it seems too small, but my body weight squat is just a rough analogy. Certainly that number is not too big. Maybe you could argue it's a little bit too small, but it didn't say that it was an Olympic sprinter, just said a sprinter. So it could be I was going to say middle school sprinter, but 61 kilograms, that is about 135 pounds, maybe a middle school sprinter. So one of our checks then, is the answer reasonable? I came up with a force that is similar to what we are familiar with legs being able to exert on tracks, so thus tracks being able to exert on legs. And then I also did an analysis of the units. So we just plug in, we've got kilograms, meters squared per second squared divided by meters, and then we've got newtons. So there's the kilogram meter squared per second squared divided by meters. We simplify, so a meter cancels here. We end up with kilogram meters per second squared, which is a newton. So the units check out as well. And all the numbers here had 3 significant figures, and my answer has 3 significant figures. So checks out. Let's compare that with the rubric. So we're going to visit the problem-solving rubric. The sketch has 2 parts. So first off, the parameters, so labeling the parameters. That's not a super difficult task, so that can be worth up to 1 point. So clearly stating all the knowns and translating them into proper symbols. And here I know how to easily erase that. And the picture. So let's see if clearly states all the knowns, translates the problem into appropriate symbols. So these are all symbols that we're familiar with, and they are applied here and labeled appropriately. So I think that is clearly a 1 point solution. And now the sketch, the picture, for 3 points, clear and complete picture, coordinate system, and any appropriate supporting symbols such as free body diagram. So I said we didn't really need motion diagram or energy diagrams, anything like that. So we have a clear and complete picture. We've got a coordinate system, and we've got all the symbols. So that's definitely 3 points. If I had a picture, but not very many symbols, so for example, I had this picture and only a couple of the arrows. Let's say I drew the force of the wind on the person, the force of the track on the person, didn't really label, show a track, label any sort of directions, positions, that would be worth maybe half credit, potentially 2 out of 3 points or 1.5 out of 3 points. And then the solve has 2 parts. One is, did we use the equations correctly and completely? So I have all the equations here that I need, definition of kinetic energy, work kinetic energy theorem, and then the formula for work. So all those are here, and all the steps are shown. Notice that I have everything completely stepped out. So those are having the proper equations, but then does each step flow from the previous step? So the more steps I show, the better that is. So I think definitely one step flows to the next. There's nothing out of order, and there's also nothing missing as well. So I didn't skip anything. So I'd give myself a 3 on that and a 2 on that. And then the check states a clear and accurate justification and then answers the question correctly. So I want to know the force that the track exerts, and that's what I answer. Sometimes you plug in all the numbers correctly, but you don't solve for the final thing that you want to solve for. That would be worth fewer points. And typically, I like two separate justifications. Significant figures by themselves, that is not a legitimate justification. But if you check the units in the significant figures, I'd be okay with that. Definitely, the most preferred is a number that makes sense given the context. And pushing off with 23 pounds, again, maybe seems a little bit too small, but it's not 1 pound and it's not 400 pounds. So that is my overview of things. Here is the rubric. Again, I labeled everything properly. I drew a sketch that shows everything. I listed all the proper equations and used them properly. Didn't skip any steps. The flow makes sense. And I have 3 ways to justify my answer. So this would be a 10 out of 10 points using the problem-solving rubric. Thank you.